Oh, and so I have gotten a couple of emails from people who are saying that their Pearson isn't working. And I need to confirm this, but right now my idea is it's been 2 weeks since the courses started officially. And if you haven't bought the book or the access, but you've still been using Pearson, I think what's happening is that Pearson will give you a 2 week like trial period before they'll actually start, blocking access. So if you have never bought Mastering Chemistry or the ebook before and you've been using Pearson thinking, oh, hey, I don't need to buy it anyways, and then you pop into Mastering Chemistry and, oh no, it says I need an access code now. I'm pretty sure that's the reason. So just to make people aware of that in case you run into that as well. So on Wednesday, I am aware that we had one more problem to do on that PowerPoint, the cumulative, like bonus, this is a really hard unit conversion type of problem. And so we're not going to go over that in class just for time. And also, it is more difficult than what I'm going to ask you to be able to do. I will say, if you want to go back to Wednesday's lecture, problem 3, if you can do that unit conversion and get the right answer, there's nothing in this class I can ask you about unit conversions that's nearly as hard as that question. So it's a good way to challenge yourself. But that being said, we're going to move on. And today we're getting more back into the non-math side of chemistry. And we're going to talk about bonds, chemical bonds. And so when we think about compounds and molecules, the force that holds these atoms together, we call the chemical bond. And what a chemical bond is, it's simply magnetism, right? We talked about in the atom how the center of the atom is full of protons, positively charged. In the outside of the nucleus, you have this cloud of electrons, negatively charged. Well, when two atoms come together, you have attraction between these charged particles, the electrons and protons, and you form this force that holds the atoms together. And we have two types of chemical bonds that we're going to talk about, the ionic bond and the covalent bond. All right. So an ionic bond is between metals and nonmetals. So I'm just going to do a mock-up of the periodic table just so we can remember. So there's kind of what the periodic table looks like. And there's this like little ladder on some periodic tables. Everything over here is a metal, and everything to the right of the ladder is a non-metal. So we already talked about that. And when a metal and a non-metal react together and form a molecule, they create what's called a ionic bond. Because what happens is that the metal atom, so that's my metal and non-metal atom, the metal atom gives an electron to the non-metal atom. So electrons are negatively charged. So what happens is that the metal becomes overall a positive charge. The non-metal overall becomes a negative charge. Now you have something that's positive, something that's negative. They attract and they stick together. That's why I have, think like magnets, right? If you stick two magnets together, as long as they're opposite poles, plus and minus, the magnets stick together and they're very hard to separate depending on the strength of the magnets. That's how an ionic bond works. A metal gives an electron to a non-metal. Now they are bound together. The other type of chemical bond is the covalent bond. And this happens between nonmetals. And this is more like a sharing of electrons, where you have two nonmetals. And if they each have an electron, what they do is that they will each put an electron between each other. And now they share these electrons. And they're connected through this bond of sharing. And classically, the way we think about that is that they're connected by like a spring. These two electrons hold these atoms together like a spring, where they can like vibrate back and forth, but it's very hard to break that spring because the electrons are like that bridge holding the nonmetal atoms together. So that's what I mean by sharing. They share electrons, and that's called a covalent bond. So any questions about our definitions there? All right, so we can move on then. So let's talk about compounds now. A molecular compound is when you have two or more nonmetals that have a covalent bond. And the basic unit of molecules are the atoms that make up the molecule. For example, water is made out of H2O molecules. So water, oxygen, hydrogen, hydrogen, all nonmetals connected through a covalent bond. This line is a covalent bond, and it represents two electrons. Carbon dioxide, again, more nonmetals. Each line is two electrons. This is what we call a double bond. So between each oxygen and carbon, you're sharing 4 electrons. Then you have something a little more complicated like propane, which is C3H8. Again, all nonmetals, all covalent bonds. They are all molecular compounds. So if you have nothing but covalent bonds or nothing but nonmetals, we call that compound molecular. While if you have ionic bonds, that is, if you have a metal plus a nonmetal, we call that an ionic compound. So cation, which is positive, anion's negative. So cation would be your metal, anion would be your nonmetal. They come together to form that ionic bond, to form an ionic compound. We call the unit the formula unit, which is the smallest neutral collection of ions you can make. For example, for table salt, the formula unit is NaCl, because 1 sodium and 1 chlorine, sodium is positive, chlorine is negative, they equal to a neutral charge. It's not always going to be 1-to-1. For example, MgCl2. Mg is +2, Cl is -1. So you need 2 Cl's to balance out the +2. So the formula unit of magnesium chloride is MgCl2. Right, so any questions about those definitions? All right, then we can move on. So here's a question, and I have a poll for this. I have 6 compounds for you, and I hope you have your periodic table out like always, but I have 6 compounds for you. I want you to tell me, are we looking at an ionic or molecular compound? So that's what the poll is going to be. And for any ionic compound that you are able to recognize, tell me what the cation and anion is, and then based on what we talked about on Wednesday, tell me what the charge of the cation and anion will be. So let me pop up the poll. And I will give everybody a few minutes to work through this. As always, if you have questions, let me know. Make sure you are trying to guess the charges of any ionic and or any anion and cation you say for your ionic compounds. So we'll do about 30 to 40 seconds on this. So make sure if you haven't yet, get those answers in. Make sure you have charges. Then we'll go over it in a second. All right, so let's take a look at this. So there was some variation here, but let's just go over this really quick here. Email, please get out of the way. All right, so CO2. Well, this was one of our examples that I just went over on the previous slide. So hopefully you were paying attention for that. But carbon and oxygen are both nonmetals. So anything that's a nonmetal forms a molecular compound. While nickel and chlorine, chlorine is a nonmetal. Nickel in the middle there, element 28, is a metal. So a metal plus a nonmetal make a ionic compound. In ionic compounds, the metal is always a cation. Remember, cations are positive. And the chlorine is the anion, a negative ion. Okay, so chlorine is a halogen. We talked about this on Wednesday, but halogens are always -1 charge. They just always are in a compound. Now, for nickel chloride, I have 2 chlorines for every 1 nickel, right? So the math is the charge of nickel plus 2 times -1. So this is representing my chlorine charge. Chlorine is -1, and I have 2 of those. They have to equal to 0. So that's the math I do to figure out what the charge of nickel is. And so nickel has a charge of +2. All right. So nickel is +2. C, sodium iodide, metal and nonmetal, ionic. Sodium is in our first column. Things in our first column always have a +1 charge. Iodine is a halogen, column 7A or column 17. Anything that's a halogen always has a -1 charge. PCl3, all nonmetals, molecular. CF2Cl2, all nonmetals, so molecular. CCl4, all nonmetals, so molecular. All right, now that you've had some practice looking at these, does anybody have any questions? Want me to explain something else again or anything at all about determining whether a molecule will be an ionic compound or a molecular compound? Yes, so question, I gotta find you. Okay, so I can unmute you if you'd like, or you can just type it in the chat since you raised your hand.
You can unmute me.
Yep, I can hear you now. I guess you don't want to be unmuted. That's fine. But so you have a question then? Try this again.
Yeah, it wouldn't let me unmute. Sorry.
Oh, yeah. Okay, it should be fixed now. So go ahead.
Okay. So you described the positive and negative charges for the first couple on that question there, A, B, and C. Can you do the bottom 3 now?
So those are molecular compounds, so they don't have charges.
Oh, you're right.
Ionic
Okay.
compounds have charges. Everything else is neutral in a molecular compound.
Okay, so we don't have to worry about that on that one. Okay, sorry about that. Thank you.
No, of course. Never feel sorry about asking questions. So I'm just gonna, there we go. All right. So let's move on then. All right. So now that we've seen molecular and ionic compounds, we're going to look at formulas now. So we have things that are called molecular formulas and an empirical formula. So I'm just looking at the top. A molecular formula is every single atom that's in the compound. So butane is made out of C4H10. An empirical formula is like, what is the best way to describe it is that I take my C4H10 and I divide it by the highest common, I think, denominator. I forget the actual word on the top of my head, but what I'm doing here is you do C4 and H10. Well, they're each divisible by 2. You get C2H5, and you can't divide 2 and 5 again and get whole numbers. Same thing for 8 and 18. Divide each by 2. You get a 4 and a 9, C4H9. All right. So one of the questions I always get is, people understand molecular formula. It's every single atom in a molecule. That makes sense. Why would we ever use this weird thing like an empirical formula where it's like, I know the ratio between atoms. Like for every 2 carbons, I have 5 hydrogens, or for every 4 carbons, I have 9 hydrogens. Why is that ever useful for us? And the reason is the empirical formula is what you can get out in experimentation, right? So if you do an experiment and you're trying to figure out what a compound is, so experiment, usually you'll find out the ratio of things. So if I give you like octane, you don't know what it is. When you do an experiment, you will find that for every 4 carbons, I have 9 hydrogens. So usually when you do those experiments, you find an empirical formula, and you have to do another experiment to do a molecular formula. Throughout this course, we're mainly going to care about the molecular formula. There's going to be a few instances where we look at the empirical formula, but they're going to be rare, and I'll make sure to really point those out. Right. At the bottom here, we have our structural formula. So structural. And this just shows you how things are bonded. So here we have HOOH, or you can just do it in a line. I know it's cut off at the bottom there for you, but it's just showing the same thing again in a line. Either one is fine. And if you're wondering, that's hydrogen peroxide. For those of you who are going on to organic chemistry, once you're finished with me, you're going to be seeing these compounds a lot. These are our hydrocarbon compounds, just carbon and hydrogen. A lot of the times, chemists are super lazy, and so we don't draw out H's if they're bound to a carbon. So that's why these two things are actually equal. Anytime in chemistry or a compound, if you see a line like that at an angle, that means carbon. Always that means carbon. Any line that ends in a point also means carbon. And although not shown, and this is something you'll learn in organic, carbon always needs to have 4 bonds. So if nothing else is shown, hydrogen is implied to be there. It's just a way to save time when writing for chemists, because this is way faster than doing this, right? So chemists have their own shorthand when it comes to carbon and hydrogen. And I did mention this a little bit when I was talking about molecular compounds, but the number of bonds actually matter. Like the number of times we draw a line means something. So a single bond means you share 2 electrons. A double bond means you share 4 electrons. And a triple bond means you share 6 electrons. And we'll talk about later on in the semester how to know, when to put a single bond, when to put a double bond, when to put a triple bond. That usually comes at the very end of the semester. But for right now, as long as we can look at these pictures and recognize what's going on, that's good enough for the beginning of Gen Chem 1. Another way that you'll have to look at molecules is in this sphere notation, where we give each atom a sphere, and then based on what atom it is, we give it a different color. So what I want you to do is I want you to look at these images and try and determine what the formula of the compounds are. Your keys on the right, just so you know, you don't have to memorize like the color code key here. If I ever do something like this, I will give you this key, but see if you can take a minute or so. And I'm just rewriting these molecules, but tell me what molecules are we looking at for A, B, C, and D? So take a minute, see if you can figure that out using the key on the right. The molecular formulas. All right, so hopefully you had some time to try and decipher what type of molecules we're looking at. And depending where you go on science, you're going to see molecules represented like this all the time. So in A, this black sphere is carbon, and it's connected to 3 hydrogens. So that's CH3, and that's connected to another carbon, C, connected to CH3. So that's what we're looking at. However, usually you don't write your molecular formulas as CH3, CH3. You combine the like number atoms, and so you get C2H6. So another question that I usually get, doesn't matter what order you put atoms in, like what if I answered H6C2? Is that still correct? And it is correct. It just looks odd to a chemist. Usually hydrogen goes after carbon. And usually a hydrogen at the front of the molecule means that hydrogen's an acid. but technically it's not wrong. It's just odd. So you can put it whatever order you want, and I won't mark it wrong, but just so you know, moving forward, usually it's like carbon and then hydrogen. Usually you put your center atom first. So for B, this is nitrogen, oxygen, oxygen, and O2. Again, I'm putting my center atom first. C, that's sulfur, oxygen, 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 SO3. Then for D, sulfur, hydrogen, hydrogen, SH2. So there are the molecular compounds for these 4 atoms. So any questions about how to read formulas when we are looking at sphere representation? Okay. And I will say that even though I'm not going to have you memorize the colors because that's not like useful, just know that usually these color schemes are kind of normal. So carbon's usually black. I've seen it as green before, but it's usually black. Hydrogen's like always white. Nitrogen's like always blue. Oxygen's always red. Sulfur is usually always yellow. The other colors change depending on the person who's doing it. But usually those like 5 are more or less consistent, no matter what text or like image you're looking at. Usually people stick to at least those color schemes. All right. Now let's move on to the polyatomic ions. I always found this to be the one of the interesting things of chemistry, because once you learn polyatomic ions, you can start looking at the ingredients on anything you buy, like in the grocery store, and start making sense of what's actually in there. Because I always find it funny when people are like, I don't want to eat this food. This food has things in it I can't pronounce. And then you learn chemistry and it's like, oh, that's just a fancy word for a salt. Yeah. Okay. Anyways, many ionic compounds are not just simply like 1 sodium and 1 chlorine. A lot of ionic compounds contain a molecular compound plus a metal, right? That's what we call polyatomic ions. Just so we break down the word in case you're not quite sure what poly means, that's like many, right? So many atoms ion, polyatomic ions. If we look at an example for bleach, the active ingredient of bleach is sodium hypochlorite. We'll learn next week how to read the word hypochlorite and figure out what that means. We don't need to do that right now, but to show you what sodium hypochlorite is, so sodium, so it has sodium, and this molecule, ClO, that is hypochlorite. So here we have a metal, and these nonmetals are in a covalent compound. Now, this parenthesis means this forms a covalent compound. That's not always the case. You could also write sodium hypochlorite as NaClO without the parentheses. And that would be fine too. So the rule of thumb is, if you see metal and then following that metal is a bunch of nonmetals, you can safely assume those nonmetals are in a covalent compound. That's not always going to be the case. There are many exceptions. But if they're like, usually it's safe to assume that, especially if they put it in parentheses like this, that means like almost always that's a covalent compound. Those of us who like potato chips, you might see on the back of the ingredients, monocalcium phosphate. Well, phosphate is another molecular compound, so PO4 plus calcium. Now, how to figure out the charges of these polyatomic ion compounds? Again, we have to go back on what we learned on Wednesday. Calcium, that's in the second column. Anything in the second column except beryllium, beryllium's the exception, but everything else will always have a +2 charge. And like our ionic compounds that we talked about earlier today, polyatomic ions have to have a neutral charge. So if calcium's +2, that means all of the phosphate atoms added together must have a -2 charge. Same thing for hypochlorite, sodium hypochlorite. Sodium, column 1, so +1. Chlorite overall has to be a -1 charge for them to balance out. Sodium bicarbonate. Here's the molecular formula for sodium bicarbonate. And we figure it out the same way. What are the charges of this polyatomic ion? Sodium, like we just said, column 1, it's element 11. So column 1 always has a +1. So to balance out, everything else in that compound has to be a -1 charge. All right. So from what I've talked about so far, does anyone have questions about polyatomic ions? Want me to repeat anything? Want me to go over something more in detail? All right. So question 3 is simple. I'm just giving you the formulas of our polyatomic ions. I just want you to tell me how many atoms are in each formula. And I'll do A just to show you how this works, right? So we had Mg3PO4 2. So this 3 for magnesium is saying we have 3 magnesium atoms. For if you have, and now for the other ones, if you have a parenthesis and a number outside the parenthesis, you take that number and multiply it by everything inside. So you distribute it. That means we have 2 phosphates and 8 oxygens. The 8 comes from inside the parenthesis. We have 4 oxygens, and we're multiplying that by 2 from the outside for a total of 8. Yeah. So seeing how A is done, I'm going to give everybody a minute or two to figure out how many how many atoms each type of atom are in each one of these formulas. So take a minute, do that. If you have questions, let me know. so hopefully you had some time to get a couple of them done. So let's take a look at this. So FeNO2 2. So one Fe, because it's not in the parentheses, so it's not affected by this 2 on the outside. Distribute the 2 nitrogens, 4 oxygens. CuSO4. 1 copper, 1 sulfur, 4 oxygens. So this 4, there's no parentheses around it, so we don't distribute it. It's only affecting the thing it's directly attached to. So that's why it's 4O. Beryllium chloride, 1 beryllium, therefore 2 chlorines. Calcium nitrate, distribute that 2. 1 calcium, 2 nitrogens, 4 oxygens. So that's how, looking at any formula, we can determine the type of atom in those formulas, or how many of those atoms. So any questions about this problem or this idea? Okay, so we can move on then. Yeah, this should be the last thing. The last thing we're going to talk about is the idea between diatomic molecules and polyatomic molecules. So sometimes when atoms interact with themselves, they will form a diatomic molecule. And if you're not sure, di means 2. What I mean by that is anything in the yellow box, normally when it interacts with itself, it does so in a pair. So hydrogen, you will never find hydrogen alone as just one atom. If hydrogen's by itself, it forms H2 molecules. The same with nitrogen, like 70 something percent of the air we breathe is made out of nitrogen. But when nitrogen interacts with itself, it always forms N2. It won't just be nitrogen, like just N by itself. O2, oxygen. Sometimes oxygen forms O3. That's called ozone. But most of the time it's O2. And all your halogens, F2, Cl2, Br2, I2. So any molecule that's yellow when it's by itself will form a diatomic molecule. The elements in this salmon pinkish, like mute pink color, will form a polyatomic molecule. Remember, poly means many. So usually phosphorus usually isn't bound to one thing. Phosphorus usually binds to many things. Same with sulfur. You're hardly ever going to see sulfur just bound to one other atom. Usually sulfur is bound to a lot of things. And selenium as well. So that's what these salmon things saying. Everything else in our like really light, like brown gray type of color, when they are found in nature, like as pure elements, they are by themselves. They don't bind to other things. So like carbon for the most part is just carbon. If you find like a pure piece of carbon, it's just carbon molecules. They don't necessarily, they can be bound to each other like that, but they don't form like a diatomic molecule or anything. Metals, nickel, right? Nickel is just like nickel by itself. Iron is just iron by itself. They have their own type of bonds called a metallic bond, but they don't really form diatomic molecules. So what I really want to point out here is make sure you know what atoms form diatomic diatomic molecules. So that's HNOFClBri. That's what we need to know right now. So it's your halogens, no H. When they are by themselves, they will bond themselves. That's the most important takeaway from this, because knowing that makes your life easier when it comes to predicting reactions. So our last question for today, and I have a poll for this. These 5 elements, when they're by themselves, are they going to stay as atoms, or are they going to form into molecules based on the information we just went over? So let me pull up the poll here and give people a minute or two to answer this. Then we'll go over it, and I'll let you free from my grasp on this Friday. All right, since we're running low on time here, and we're basically out of time, I'm gonna end the poll. And it looks like the people have answered. You seem like you have it, but I'll just go over the answers here. So neon's a noble gas, column 8A. It's not a halogen, so it stays as an atom. Fluorine is a halogen, 7A. So it's a diatomic molecule when it's by itself. Lead, metals are always an atom by itself. Oxygen is one of ours that always forms a molecule with itself, as does hydrogen. So HNO FClIBr is what we are looking for when it comes to diatomic molecules or not. Right. With that, any last questions about anything before I sign off for the week? And by sign off, I'll still be available by email if you do have questions. All right. If not, that's all I have for you. I'll put up a homework as always. I hope you have a good weekend, and hopefully I will see everybody on Monday. Have a good one, everybody.